So, a bit of a change this week, Karl. Welcome to another episode of Shirtloads of Science. My name's Geraint Lewis. I'm your go-to cosmologist and astronomer. You've called me into your secret lair because you have a question about travelling in the universe.
Yes, so here's a question and answer. Assuming that you are limited to the speed of light, and assuming that the universe is pretty big, many billions of light years across, the question is, how far can you travel in a single lifetime if you can accelerate your spaceship at a constant 1g, and then when you get to the halfway point, you slow down again? So how far can you travel in a single lifetime travelling at 1g? And the answer is to the edge of the universe. Oh, come on. That hurts my head.
Yeah, let's start with that concept of a G. So let's actually talk about rockets first of all. Everyone loves to see a good rocket launch. But what we tend to forget is that the majority of space flight is done by rockets which are not firing, or spacecraft that are not firing their rockets. Rockets are fired when you want to get off the surface of a planet or you want to change direction, etc. But for the majority of space flight, you tend to just free fall. You tend to fire rockets and then just coast along until you get somewhere and fire your rockets again. So this question is somewhat different. This is considering a hypothetical rocket which can keep firing. So, you've got enough fuel, you feed that into the rocket engines, off it goes. And because you keep firing your rocket, you can keep accelerating. And in this particular case, the question focuses on a particular acceleration. This is 1g, where g is the gravitational acceleration at the surface of the Earth.
On the surface of the Earth, we all experience 1g, and apparently that's good for our bones and so many other things for our health. And in fact, people in microgravity in space have got all sorts of bad things happening. So one advantage, I'm guessing, of being able to accelerate at 1g is that, to all intents and purposes, it's like living on the surface of the Earth, depending on how big your spaceship is.
That's precisely the point. So we evolved, of course, on the surface of this planet, and so the structures in our bodies are designed, in air quotes, to function in this particular acceleration. And you mentioned this issue with regards to things like bone loss for astronauts. There are lots of things that happen to your body when you're in microgravity. And I was listening to a podcast with Tim Peake, the astronaut. He was saying that one of the things that happened to him that he didn't realize is that when you are not using your feet, then all the hard skin in your feet just gets shed because you're no longer walking on them, and your spaceship fills with all these teeny little bits of foot skin, which isn't very nice. But there's, as you mentioned, there's these other things to do with your bone structure which suffer when you are in 0g. So if you are firing your rocket at 1g upwards, that means when you're on board the rocket, you basically feel the equivalent gravitational push downwards, and it would feel like you're standing on the surface of the Earth.
Okay. When we've got the people taking off in our conventional rockets, they fire the rockets and then 8 minutes later they're up at 400 kilometres altitude, and they've changed direction. Instead of going straight up, they're running parallel to the surface and doing about 28,000 something kilometres an hour, 7 kilometres a second, and they might have hit 2 or 3 Gs on the way up. But here we've got a gentle one, just like on Earth. You're accelerating at 1g, but the thing is, you don't switch your engines off.
Yes, and anybody who's done any rocketry physics, you know that is a very expensive thing to do. But you can accelerate, if you can accelerate at 1g, it'll just be like standing on the surface of the Earth. And the big question you have, of course, is when you're accelerating like that, you're getting faster and faster and faster. And the question is, if you keep doing that, keep firing your rockets, how far can you get, say, in a typical human lifetime?
Right. So you're accelerating. I've got this mental image in my mind, not just for a few minutes, but just day after day. And the fuel, either you've got, well, forget fossil fuels or liquid oxygen, liquid hydrogen, forget nuclear. Let's suppose you've got antimatter. In fact, let's make it even better. Suppose you've got a magnificent magnetic funnel out the front, or some sort of funnel, and you're scooping up the occasional atoms, and you're picking up your fuel as you go. Regardless of that, regardless of whatever hypothetical artifice or device you use, you can accelerate at 1g, bearing in mind that the maximum speed you can ever get to is just a tad under the speed of light.
Yes, so on our journey, we are going to be accelerating. We're going to be getting faster and faster. And for much of the journey, the initial parts, the velocities are going to be numbers that we can sort of understand, right? We'll be getting up to, hundreds and then thousands of kilometers per second. Eventually, like everything, everyone's seen a rocket launch, everything goes slow at the start and gets faster and faster. This is what happens when you fly your rocket ship off into the universe. You are going to get faster and faster and faster. And eventually you'll be starting to approach the relativistic limit, right? We'll be getting into that scenario where our speeds are getting somewhat similar to the speed of light. And then we've got to worry about Einstein's special theory of relativity, which tells us that if you have objects moving relative to one another, then their clock rates will be different, right? They will tick off different rates because clocks are tied to relative motion. That's what the relative in relativity means, is that you get different effects depending upon your relative velocities. So as we head out, we won't have to worry about only the velocity, but we'll have to worry about the fact that something strange happens to the clocks on board the spaceship.
Right. Just one more background thing. Assuming that you don't want to just whistle past your target at a very high speed, halfway to your target, you're going to start slowing down. Half your journey is spent accelerating up and half is slowing down.
That's right. The idea is that if you wanted to stop somewhere, you'd get halfway through your journey, turn your rocket round and then fire it in the opposite direction. That would slow you down. And then if you kept firing it, of course, it would then turn you around and bring you back to the origin, and you spin your rocket round again and keep firing it. And hopefully that would bring you back to rest where you started from.
Okay, let's just do the first part, getting out there. You mentioned the relativistic part, and I've had a few people talk to me saying it just doesn't sound right that your clocks run more slowly as you go faster. Then this is running from memory. I could be wrong, but my memory is that if you're at the Large Hadron Collider on the border underground of Switzerland and France, and the hadrons, the hydrogen ions, are moving at 0.999991% of the speed of light, my memory is that 1 second for them is 11 months for you and me. So time is slowing down massively.
Absolutely. And it's not only the Large Hadron Collider where you have to worry about this. Most of your listeners will have a smartphone, and on their smartphone they will have a GPS system. And a GPS system is really your phone listening to clocks on satellites and using that to calibrate your position. But if you're going to listen to clocks on satellites, you need to know how they're ticking, and how they tick depends on their velocity. And you said satellites are traveling at 7 kilometers per second, which is a lot slower than the 300,000 kilometers per second that light travels. But if you want accuracy in your GPS, then you need to worry about the speed of your satellites. So it's not just Large Hadron Collider, it's everyday life you've got to worry about this.
You will then start traveling faster. You're accelerating at a constant rate, and you've got your machine. And so the figures are that if you've got a clock on your spaceship, to get to Proxima Centauri, the nearest stars, and by the way, I got this from an article in Forbes magazine called How Far Could a Spaceship Go If We Never Ran Out of Thrust by Ethan Siegel. But blow me down, you've written on this before that. Back in May 15, 2016, for Cosmic Horizons, you wrote, how far can we go? ? A long way, but not that far. And then in, what do you call that thing, R of X, or what was that?
Where the physics papers go.
And you've written The Adventures of the Rocketeer, accelerated motion under the influence of expanding space by Juliana Kwan, Geraint F. Lewis and J. Berrien James. And that was, if you want to remember it, written on the 9th of the 9th of the 9th. To get to Proxima Centauri, which is about 4.3 light years away, the clock on your ship would have ticked only 4 years because of the slight slowing down.
That's right. You would basically get up to relativistic speeds relatively quickly. And to yourself, it would only take you 4 years to travel between here and the nearest star if you could accelerate at 1G.
And then if you take it further, you're going for Sirius, 8.6 light years away. It would take you 5 years on your clock. And so you're now beginning to get some serious time saving.
Yes.
The Orion Nebula, 1,000 light years away, that's only 15 years, not 1,000 years, 15 years, 1-5. The centre of the galaxy, 27,000 light years away. That's a black hole. What's it called again?
Sagittarius A star.
Okay, so to get to 27,000 light years is going to take you 20 years, and then wait for it, to travel 18 billion light years will take about 45 years on your clock time, on your spaceship time.
That's right. So we have to be careful now because we're going to be moving into another regime. So firstly, as we mentioned, we are traveling faster and faster. So we have to worry about Einstein's special theory of relativity. But eventually, once we break free of the galaxy after, this 15 years or so, and we're now traveling through intergalactic space, we have to worry about the fact that the universe itself is expanding, right? Space is expanding. And so we also bring in Einstein's general theory of relativity, which tells us how gravity works. And that then has an additional effect that we need to worry about when we're going to be traveling through the universe. So as you travel outwards, you're trying to reach distant objects, but those distant objects are also accelerating away from you because the expansion of the universe is accelerating. And when you put all of that together and you swish the numbers around, you get that you can travel out to roughly 18 billion light years in a typical, journey. In a human lifetime, I think we took 100 years or something. You can get a little bit further, but that's sort of the scale at which you can get out to. And what will happen, as you mentioned, is that the first part of the journey will be relatively slow, a couple of years to get to the nearest star, 15 years to get outside the galaxy, but then suddenly you're traveling really fast, that whoosh, before you know it, you're at 18 billion light years.
But you mentioned then the expansion of the universe. So will the expansion of the universe be fast enough to carry things away from you that you can't get there? But secondly, is the expansion of the universe something that is greater between the galaxies, but lesser inside of a galaxy because the gravity of the galaxy is overcoming it or reducing it to some degree?
Oh, you're entering a philosophical minefield here. Essentially, one way to think about it is that inside a galaxy, gravity is strong enough to be the dominant thing going on. Between the galaxies, that's when you feel the fact that the universe is expanding. So we have a galaxy next door to us, the Andromeda Galaxy. It's a little bit bigger than us, about the same size. They're hurtling towards each other at, hundreds of kilometers per second. They're going to collide. They only really care about their own mutual gravity, not so much what else is going on in the rest of the universe. But we've got our galaxies in something called the local group, and there are other groups scattered around, and in each group they care about what's going on. But between them, the expansion of the universe is driving them apart further and further and faster.
Right. So is it fair to say that the expansion of the universe, which is 70 or so kilometers per second per megaparsec, am I roughly right?
Yes.
Yeah. Is that expansion less within the body of a galaxy?
Within a galaxy itself, you would say that space itself doesn't really expand. Again, you might need to come and do my general relativity class later in the year. This is where things get a little bit messy. You have to be very careful about what you're defining here. The way you should think about it, inside galaxy, space isn't really expanding. There's a lovely article written by Professor John Peacock at the University of Edinburgh, and it's called A Diatribe on Expanding Space, and he goes into these arguments about, is the space in my bedroom expanding? And if it is, what does that even mean? And you realise that there are some subtleties involved. But broad brush picture, space inside the galaxy isn't expanding, space between the galaxies is. And if you've got some relativists listening to your podcast, I know they're probably grinding their teeth at that statement, but it'll do for now.
Okay, I'll give them something else to grind about. Centrifugal force. Ha ha ha. Okay, now the second one. Does the expansion of the universe mean at some stage it's limiting how far you can go?
Absolutely. That becomes the limiting factor of how much we can explore the universe. It might seem slightly bizarre, right? That as far as we can tell, it looks like the universe has got an infinite future ahead of it, that there's an infinite amount of time. And you might think, well, if I just keep accelerating and I have this time dilation effect, as it's called, then surely I can explore everywhere eventually. If I can accelerate even harder, I should be able to go further, etc., right? But that's not quite how it works. The expansion of space itself becomes the limiting factor, and there are objects which we will never be able to reach because they will always be accelerating away from us faster than we can accelerate towards them. And in effect, what will happen in the distant future is we will feel like we, what's the statement from, is it Alice Through the Looking Glass? I'm trying to remember, about the Red Queen, about how fast you have to run to stay in the same place. It will be a similar kind of thing, is that you'll be expending all this effort, but eventually you won't feel like you're getting anywhere because the universe is expanding away from you.
So you have to keep on running as fast as you possibly can just to stay where you are.
Yes.
So the expansion of the universe will limit how far we can go, even if we have a ship that can accelerate at 1G, if we are constrained to a maximum speed of the speed of light.
Absolutely. If you think about it, it's the same is true for a beam of light. Even though there's an infinite future ahead, I can turn on a torch and shine light out into the universe, but it's only going to be able to travel a finite distance away. It will never reach certain objects because they will accelerate away too fast.
Wow. But let me get this straight. I can travel many billions of light years in one human lifetime. I can still be alive. My body will keep on going for 45 years, and I can get virtually to the billions and billions of light years there because of relativity slowing my ship's clock down.
Yes, and we should be very careful about what we mean here. When you say slowing the ship's clock down, it's not just that the clock ticks slower, but everything that ticks slower. So your body, everything there, your heart rate will be correspondingly slower as seen by somebody outside, right? The heart rate will be correspondingly slower, the way that your neurons fire. So on board the ship, you just think everything's fine. But relative to somebody else, your clock, being even your internal body clock, is all ticking slower.
Okay, I feel happier that I can travel in one human lifetime to the edge of the universe. Okay, part 2. Can I get back? Ignore the fact that everybody's gone and died and crumbled into dust after billions of years, but can I get back to where I took off from?
Only if you time everything precisely, right? So let's pretend that you want to travel out, turn around and come back. You can do that. You can work out, and I think we did that in that publication that we wrote all those years ago. You fire a rocket, turn it around, slow it down, turn it around, come back, etc. The problem is that if you miscalculate the turnaround by even a little bit, then on your journey back, you are now battling the expansion of the universe. And if you've left it too long to turn around, then suddenly the Earth might become that point just outside where you'd be able to reach. You could do it, but you just have to be very judicial with your timing and have to understand the underlying expansion of the universe correctly enough. But it said if you miss and turn around, then suddenly the Earth becomes a point that you will never reach, even in the infinite future ahead of you.
I've started reading some science fiction back from 1948. I accidentally ran across it. And I'd like to be able to travel in a spaceship somewhere. Do you still read science fiction and love to travel somewhere?
I do read science fiction. Currently reading apocalyptic science fiction, which I quite like. I'm more of a fan of time travel than I am of zipping through the universe. But you have to remember, what we're talking about here is motion of a physical rocket that's firing, material at the back of it and is bound by Einstein's special and general theories of relativity. Okay?
Yep.
You can bend the rules somewhat, right? What we have said so far is that we are basically just like a particle traveling through the universe, and we are doing whatever the universe tells us to do. But Einstein's general theory of relativity tells you that space and time can be manipulated, right? You can manipulate space and time. You can bend and stretch space and time by changing distributions of mass and energy.
Yep.
And in fact, you can bend and stretch time and space such that you can build... The nickname is a warp drive, right, from Star Trek. This is an idea that was first published in the early 1990s by Miguel Alcubierre, who showed that you can manipulate space and time to have a warp drive that can travel at any speed. So it's no longer constrained by this notion of what can light do in the universe, because what you are doing is actually bending and stretching space and time themselves such that you can end up traveling at any speed. So it's theoretically, it's possible. Whether or not we can actually build a warp drive, that's another question altogether, because there are issues to do with the kinds of energy that you need and how you would concentrate it that would allow you to have a warp drive. So we have solutions, we just do not know if we could actually ever build them.
On that cheerful note, I will finish off with the comment that how far can you travel in a single lifetime at 1G? And the answer is to the edge of the universe. Oh my God. Look, thank you for taking us down this